So moving ahead, so the next speaker would be Francesco Incelli.
Say that I'm very pleased to be with you guys today, and I'm honored to discuss my findings with all of you and possibly get some comments. All
Absolutely.
right then.
Please go ahead. Go ahead, please.
Yeah, so now you should see the presentation full screen, I would imagine. What I'm presenting today is part of my PhD research thesis, which is called Reversible Skins Building Envelopes Beyond Time and Destruction. The title of the paper is actually Circularity in Architectural Design by Hierarchy of Disassembly. The thesis is developed, I'm a PhD student of the University of Venice, and it's partly developed with a co-supervision of Professor James Campbell, Department of Architecture, Cambridge University, and also an industry partner, which is AKT2 London, a design firm in central London. Now, the key concept of this research is how to apply the circular economy to a concept design. So, and this is where it all started. Since we did that, I started to sort of having a look at the methods for application of circularity in construction concepts like the design for adaptability, design for disassembly, design out waste, and building as a bank of material. Why are these important? Because the construction industry and architecture is part of it, produces nearly 41% of the total solid waste. So if we manage to find the way of implementing circularity, reuse, and disassembly into architectural design, but also concept design, this would definitely create a huge deal of advantage and reduction of all of the associated environmental cascades of the production of such a high amount of waste. There are some obstacles. Obviously, circular economy in architecture implies a complete change in the use of the design process. Now it comes very late in the design process, and what we want to do is to apply circularity in the concept. And also there is a heavier involvement of multiple stakeholders at concept design stage. And there is a lot of fragmentation of methods. Designers don't really have a unique or a shared approach to circularity in design. And it's also considered in architecture and construction some kind of niche design method. And the biggest one, which is last, is the cultural bias due to consumerism and the dominance of the linear economy in architectural design. So as soon as I started thinking about how to implement it, the next questions came out, and those were, how do we measure it if we want to make it effective, and how is circularity going to shape architecture somehow? Now, I started reviewing some of the standards, or either industry standards or highly used standards for circularity calculation protocols. One of them was the material circularity indicator, with its sort of whole product approach, which covers from procurement to disposal of materials. And also the other one was levels, which is part of the work of the European Commission for creating a standard for sustainability in the European Union, and specifically the indicator which is called design for deconstruction, which was quite useful because it promotes in its text what's called a hierarchical technical decomposition of a building, considering a building not just one piece of things glued together, but as a compound of materials which are then organized into components, then subsystems, and then a system level. So, but deconstruction 2.4, the design for deconstruction, focuses more on the end of life rather than the procurement and disposal, just the end of life. So what were the limitations identified in this case? I had just highlighted the main ones. The fact that circularity could be achieved in different ways at each level of hierarchy. Okay, and this is not exactly what at the moment the protocols seems to promote too much, except levels in a way. But focusing just on the materials as a way to, it could lead actually to unrealistic scenarios for the applicability of circular design as an industry standard. We know that we have different types of materials, so we want to focus more on how those materials are connected together rather than the nature of the material itself. Why? Because if they are connected reversibly, we can reuse them almost indefinitely. Now, we came out with this, what we call the circularity assessment by hierarchy of disassembly, which is based on substantially using the technical decomposition of a building and calculating the circularity at different levels. So the building can be thought as a single piece, like the functional unit. It can be broken down into walls, floors, roof systems, and etc. And those systems can be broken down into constituent parts. So it's like increasing, going deeper and smaller into with a lens into the building and sort of checking how the different parts, components, materials, they are related together. This was very much an experiment because we didn't know what we would find. And this is a representation of the sort of, I wouldn't call it protocol, but it's more of a methodology of application for existing protocols in a slightly new way. So dividing a building in what are its constituent parts, running the protocols, MCI or levels, and then comparing the results. So what we have seen, we ran these protocols for some case studies. One of them is the emergency housing for the elderly, which is designed with a DFT and complete reuse approach. Another project which is called Help Veneto, which my university also collaborated in developing, which is based on, again, DFT and complete reuse. Some other cases coming from other designers, like in this case, the People's Pavilion, which is based on reused DFT and complete reuse, but also in circular procurement. And then another pavilion, which is Vietnam Pavilion. Now, I'm not going to show all of these ones because I don't really have time for that, but I ran this process through these protocols for many other case studies. And what are the results? So very briefly, and this is the example for Help Veneto, we found out that calculating circularity at different hierarchies of the disassembly, which means for the materials, then for the other components, and then for the elements, and then assemblies, gives different results. So there is not one number for assessing circularity, but there are many, so there are at least like 4 levels, 4 hierarchies that we can find in a building. And also, what we have seen is that the only case that didn't really give any difference, any big difference, was the one that was designed with a procurement, like circular procurement and circular disposal. So it was substantially a building that was completely loaned and then sent back to its origin, and it was substantially fully circular. That's why we were sort of pleased to see that the intent of the designers was actually reflected into the scoring that we found out after the assessment. What we have seen is that MCI and L24, which are the 2 protocols that we have compared, they tend to give usually different results. L24, which is levels, gives more generous results, let's say. MCI is a bit harsher. So for us designers, and I'm going to conclude, what we will need to do is to try and encompass the architectural design through the different levels of structural connectivity. And also it's important to consider different assessment protocols that can, and these 2 can also be used as assessment tools, but also as a concept tool. So if we look at how at the moment the application of circularity comes into the design process, this comes at the stages 4 and 5 of the RIB plan of work, which is the standard for planning the development of architectural design. But what we are suggesting is that instead of doing it at stage 4 and 5, we should be doing it in stage 1 and 2. So prepare not just one architectural concept design, but like 4 concept designs, which will be coupled with a reuse strategy for materials, for parts, elements, and components. And this is obviously just a very quick overview of the findings and all of the things, the information that you can find in the paper. And this is the end of my presentation. I will also leave you my contacts in here for those who want to reach out and ask for more, because there is obviously a lot more behind it that I didn't really have the time to explain today. But I still hope that I gave you some interesting suggestions. Thank you.
Oh, so thank you very much, Francesco, for that for the presentation. So, okay, I think there might be some questions in the Q&A. Probably at your time, you can always go through them. But I do have one quick question.
Yeah.
So I think right now you're proposing that. Correct me if I'm wrong. They're proposing that the use of materials that is reusable, it's much more effective for architectural design, right? That's what you're proposing. Is that correct? So now that comes to mind because what I always think about is the cost itself, the cost effectiveness of a thing. So is it really cost effective for the designers to use the reusable materials than using the one that is not reusable? So what are your thoughts on that?
So yeah, the point is that it depends obviously on the markets, but the main point of what we are, because there are, you know, across the globe there are different markets. In some areas, some materials can be sourced more, you know, they're cheaper than in other situations. But and that's when our reflection started, because what we were thinking is, what do we do if we have a material that's substantially highly environmentally impactful? Okay, but then how can we avoid that material to be completely destroyed at the end of its design life? Because buildings at the moment are designed with a design life of 50 years, which means that every 50 years, designers are expecting that building to be taken down, produce a lot of solid waste, and then all of that rubble. It's actually very good material, which is producing pollution. Whereas we think that, it's not that we think, but we are sort of trying to demonstrate how looking at how the materials are connected together in a building and improving the fact that this building could be disassembled, that then may be transported and reused somewhere, can actually reduce the environmental impact and, you know, all of the environmental impact of it significantly. And also, in terms of cost, for instance, if it would become an industry standard to reuse parts of buildings when they're not needed anymore, this would obviously become a cheaper process. At the moment, it's actually easier to demolish a building rather than dismantling a building. So there is a systemic, and this is also, you know, one of the findings that we are realizing. Technically, as designers, we have all of the tools to design reversible buildings, okay? To design buildings that can be dismantled. What's lacking, what the industry is lacking at the moment, is a system that allows us to take those disassembled parts and bring them somewhere in a seamless way, because obviously we cannot really leave materials left outside for durability, but we need to have like a quick replacement and a quick transfer of materials to avoid them to be to improve their durability. Otherwise, this is not going to be possible. And it's so systemic. It's so based on the economic system, really, not just on this technical aspect. And it's quite interesting to find that starting from a technical perspective, we ended up on a systemic finding, saying that, you know, actually, the problem is the system we are in, not the tools that we have, because we have all of the tools for circularity in architecture.
Well, that's very interesting. Thank you for sharing your perspective with us.
You're welcome.
So, so